Block 4 is about matrices, and our study of matrices begins with networks like this, taken from Section 1 of Unit 1. As you'll remember, we have certain quantities A and B, say gallons, flowing through pipes according to certain proportions, and we want to know how much comes out. Well, that calculation is very easy. What we want to do here is to represent networks using matrices. And we'll use the matrices to help us with combinations of networks, not just single ones. So I guess I'd better begin by telling you what I mean by combinations of networks. Suppose then that we have another network, this time with 3 inputs. And here's our first network again. In both networks, there's a single pipe from each inlet to each outlet. Now suppose that what comes out of the left goes into the 3 inputs of the right. This is what I mean by a combination of networks. Notice that now there are several paths from each inlet at the top to each output at the bottom. And how to calculate the outputs now? Well, you just use network arithmetic. You multiply proportions along each path, and you add what comes out at the bottom. That is, you take each inlet and each outlet, such as these 2, the ones on the left, and you do a computation. You say that 2/5 of A flows this way, and 1/6 of that flows down here, so you multiply 2/5 times 1/6. But you do that for each path. 1/5 times 2/3, and 2/5 times 1/4. Then you add those results, and that tells you the proportion of A that gets to this outlet. But you must do that for each inlet and outlet pair. If that one, that pair, and finally that pair. And at the end of all that, you know the proportions of A and B which make it to each of the outlets. And that's network arithmetic. It could be tedious if the network were large and complicated, but the principle is very simple, which is why we began the block with networks. Because you see, network arithmetic is exactly the same as matrix arithmetic, and the combining of networks is the same as the combining of matrices. Now, matrix arithmetic and the combining of matrices is extremely important. There are a whole host of applications, and you'll be seeing some of them later in the block. But our purpose now is to look at the combinations of networks and how that can lead us to the combination of matrices. So we're going to have to find out how matrices are associated with networks. We're going to have to take a single network, such as the top one here, and ask, how can that be represented by a matrix? To show us that, here's Lance.
Well, the way we represent a network by a matrix is by analogy with the idea of functions. Let me explain using John's first network. Let's first simplify the diagram just as we did in the text, using lines instead of pipes. And let's call the output quantities U, V, and W. To see the analogy with functions, turn the network on its side. So now, our input is on the right, being acted on by the network to produce the output. The analogy here is with a function f acting on an input x to produce an output y. We represent the 3 components with 3 matrices. Our output matrix contains the quantities U, V, and W, and our input matrix the quantities A and B. And the matrix for our network will contain the 6 proportions, not just as they are, but rearranged in a rectangular pattern. In fact, we choose to arrange them in 2 columns. In other words, the first column are the proportions for the first input, A, the proportions into which A gets divided. And the second column gives the proportions into which the second input B gets divided. Now, why do we choose to arrange the proportions in this particular pattern? The columns corresponding to the inputs. Well, partly it's convention, but it is a sensible pattern. Look at the 3 rows of the matrix. They correspond to the 3 outputs. The first row corresponds to the first output, U. It gives the proportions flowing towards U. 2/5 of A and 2/7 of B. And the second row corresponds to the second output, V, in the same way. 1/5 of A and 1/7 of B. And similarly, the third row gives the flow towards the third output, W. W is 2/5 of A plus 4/7 of B. So once we've arranged the columns to be the proportions flowing away from each input, the rows automatically give the proportions flowing towards each output. And that'll work for any network. But what about this acting on? Well, I've said it's similar to a function acting on an input. But we must spell out what acting on means in terms of matrices. To do this, you've got to be very clear how rows and columns correspond to the paths in the network. So first, let's go over that again. The first column corresponds to the first input, A. It gives the proportions flowing from A. And the second column gives the proportions from B. And once the columns are written like this, the rows automatically correspond to the outputs. The first row corresponds to the first output, U. It gives the proportions of A and B, which flow towards U. So we can interpret acting on to mean that the first row is, in a sense, acting on the column of inputs, A, B, to give the value of U. And the second row corresponds to the second output, V. We think of the second row as acting on the column AB to give the value of V. And similarly for the third row. So let's see how all that applies to our second network. This time we have 3 inputs, so each output is the sum of 3 quantities. And once we set up the matrix, each output will be given by acting with each row on the column of inputs. So let's set up the matrix. Remember, we make the columns correspond to the inputs. So we look at the proportions flowing from the first input and put these in the first column. Then we take the proportions from the second input and put them in the second column. And finally, the third column. And as before, the 2 rows are going to correspond to the 2 outputs. The first row gives the proportions which flow towards the first output, P. So we think of the first row as acting on the column UVW to give the value of P. And similarly for the second row. So row acting on column just means multiply the corresponding elements in the row and the column and add the results. We have the first times the first, and the second times the second, plus the third times the third, to give this value of P. In the same way, the second row acts on the column UVW to give this value of Q. So that's row acting on column. Matrix acting on column means take each row of the matrix in turn and act with it upon the column. And that exactly mimics or models the action of a network. And it'll work for any network, no matter how many inputs or outputs, because we can always set up the matrix that describes it. Now remember, the reason we did all this was so that John could look at the way combining networks correspond to combining matrices. John.
Here's the first network that Lance looked at, and here's the matrix that corresponds to it. And the outputs of this one are the inputs to the second one, the one he just dealt with. And here is its corresponding matrix. And what I'd like to do is to combine these two matrices to produce a single matrix, which will represent a simple network equivalent to the combined effect of this large network. By simple network, what I mean is that there's a single path from each input to each output. In other words, I want to get the same outputs P and Q by replacing all the paths between input and output with just 4 paths going straight through. Well, once I've got these proportions, the alphas and betas here, then the action of this network can be expressed by these matrices. Notice that we've omitted the words acting on here. That's for convenience, really. It's much more convenient to put a matrix in front of a column and to imply the words acting on. Now, what I'm going to do is to specify, to define the combination of this matrix and this one to be this matrix here, the one which really expresses this network. And because it's so important, we've got a copy of it underneath here. You'll notice the equal sign. That's to stress the importance that we're going to combine this matrix and this one, and the result will be equal to this matrix of alphas and betas, 2 rows and 2 columns. Now, the alphas and betas are certain proportions. They're the proportions that in this network give the same output PQ as we obtain in this combined network. Well, we'd best go ahead and calculate some alphas. Look at alpha 1 here. Alpha 1 is the proportion of A that flows to P. So to calculate it, we need to look at all the paths from A flowing through to P. And now we can use network arithmetic on the 3 paths from A to P. Along the top path, the proportion of A flowing towards P is 1/6 times 2/5. Then along the second path, the proportion is 2/3 times 1/5. Similarly for the bottom path, the proportion is 1/4 times 2/5. So the total proportion of A flowing into P is the sum of these 3. Now let's see how this number alpha 1 is related to the total network as represented in the 2 matrices. We find, in fact, that alpha 1 is given by a row acting on a column. The first row of the left-hand matrix acting on the first column of the right-hand matrix. That's just using the definition of what we mean by row acting on column. Remember, you multiply corresponding entries and then add the result. And in this case, the calculation gives a value of alpha 1 equal to 3/10. That 3/10 is calculated by acting this row on this column. And the reason is that this row represents flows towards P. And this column flows away from A. And the reason it all works is that network arithmetic in that diamond is the same thing as row acting on column. And that works, of course, for the other alpha and for the betas. Let's look at beta 1. Beta 1 is the proportion of B that flows towards P. So we need to look at paths from B to P. As before, network arithmetic tells us the proportion of B flowing to P. So that's the value of beta 1. And this time, it's the result of the first row on the left acting on the second column on the right. That deals with the first output, P. And the proportions flowing into the second output, Q, the proportions alpha 2 and beta 2, are also obtained by acting with a row on a column. Alpha 2 is the result of the second row acting on the first column. And beta 2 is similar. Beta 2 is the second row acting on the second column. So it's row acting on column every time. And if you do the calculations, then these are the answers you'll get. Alpha 1 is 3/10. 3/10 of A flows to P. And the remainder, 7/10, goes down to Q. Beta 1 is 2/7. So 2/7 of B flows to P and the remainder to Q. And these numbers here depend on the fact that we're using these proportions. If you'd started with other proportions, well, of course, you'd get other answers, but it's still row acting on column. And that's how we define the combination of these matrices. But we usually use the language of multiplication. We speak of this matrix times this matrix being equal to the product matrix. And we're not confined to just these matrices. For example, in the network, there might be extra vertices or nodes in here. But then there would be flows towards P and corresponding entries in the row. But also flows away from A to them, and hence corresponding entries in the column. So still, row acts on column. And the reason is that network arithmetic is the same as row on column. So let's get rid of the numbers and concentrate on the pattern of matrix multiplication. We take the left-hand matrix and think of it as being made up of 2 rows of numbers. And we consider the right-hand matrix as being made up of 2 columns. Then we calculate the product matrix by acting with each row on each column. Alpha 1 is the first row acting on the first column. Beta 1 is the first row acting on the second column. And alpha 2 and beta 2 are obtained by acting with the second row on each column in turn. So the entries of the first column of the product matrix are found by acting the rows of the first matrix on the first column of the second matrix. And the second column is found likewise. Same rows acting on the second column. And that's how you multiply matrices, at least ones with 2 rows and 2 columns. But of course, the whole thing works much more generally. Suppose we had a third row. Then it would want to act on each of these columns, thereby giving new entries down here. There they are. But do the networks agree with that? Well, of course they do. What does this row here mean? As far as the network is concerned, it's an extra output. Well, an extra output here means there must be an extra output in the equivalent network, and that means another row. Furthermore, we might have other columns. But if we had another column, we'd operate each of these rows and act it on that column to produce a new column in the product matrix. Or someone might come along and take away one of my columns, let's say that one, leaving me with one column. Then I act these three rows on the single column. But we've seen that before. That's exactly what Lanz was doing when he was looking at the action of a network on an input.
You see, when I showed you how to interpret this matrix representation, I said the values of U, V, and W were given by acting with each row on the column of inputs A, B to give these three values. Well, the column AB is a matrix. It's a matrix consisting of a single column of two numbers. And when we act on it with these three rows, that's matrix multiplication. And this is the product matrix. It consists of a single column of three numbers. So you see, we've been doing this matrix multiplication from the start. Matrix multiplication modeled both John's collapsing of combined networks and this calculating in a single network of an output from an input.
We could end the program by exploiting this dual property of matrices, the fact that they model both the action of a network on an input and the collapsing of networks. Suppose, as we have been doing throughout this program, you're confronted with some sort of combined network such as this, and associated with it three matrices. Now, if someone says to you, multiply those matrices together, well, you can't do it. You can't multiply three things at once. You have to do them two at a time. Now, you could choose to do the first two, and then the result times the column AB, or you could decide to do the last pair, and then come along with the first one and multiply it. Looked at as matrices, it's not at all obvious whether you'll get the same answer. But looked at in terms of networks, it is clear. Let's see why. The first method, multiplying the two matrices, well, that corresponds to taking the combined network, collapsing it as we did in the program, getting the alpha-beta matrix, and then multiplying that times the column AB to give the output PQ. On the other hand, this calculation says act this matrix on the column. That's just calculating the output of this first network. The output is UVW, so we can insert that here. But then we want to multiply by this matrix, and that's just computing the output of this network, which is again PQ. So as far as the networks are concerned, the answer is PQ both ways. It doesn't matter how you think about it. The networks don't mind, and neither will the matrices. And the reason is that matrices model both the action of a network on an input and the collapsing of networks. Well, you'll have plenty of opportunity to practice and to master matrix multiplication during the block. And you'll also be seeing this triple product idea a good number of times.